Okay, so it started. So let's continue with this question. So who has like an idea about how to make the distinctions between plastic and viscous mechanical behaviors? Let's say I didn't put elastic because, well, it's very different. But what's the difference between plastic and viscous mechanical behaviors? What can you what can you think about? All right. Yes. So the one of the differences is more like what Juliana is mentioning in the chat. For the other thing that Juan Sebastian put, it's something common to both plastic and viscous. So it's not going to be like a difference. What about another difference that you know between viscous and plastic? You can think of. So anybody with another ID or bueno. So for example, if I ask you guys, what's the key property of the viscous mechanical behavior? What are you going to say? Yes. So, for example, for the viscous behavior, what's the key property that one has to consider? Hello, Camilo, Juan Sebastian, Laura, Martin. Okay. Well, for the viscous behavior, you have to look for the viscosity. But yes, of course. Um, no, you have to listen to me. I'm 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 guiding you guys in order to tell me what's the other big differences between the two. So so that's why I asked you guys what is the key property for the viscous behavior. But well, let's move on to let's move on because I have still lots of tiny little questions. So in well for the viscous behavior, it's obviously the viscosity. For the plastic, basically, maybe you've seen this this tiny little model that they do for plastic with the little block and well, this tiny little thing that you can do with little string that you can use in order to move that little block. Well, and the property for this model is the friction, but of course in reality it's not really friction. It's this is only like a little model, and actually the property for plastic is much more complicated. Yes, it's more like an activation law, but so that's a big difference um, between plastic and viscous, apart from the thing that you mentioned, that there is no resistance for the viscous. It's like the two main differences of these two behaviors, basically. All right. So, so you've seen this in the course. I would like you guys to tell me which actually answer is the right one. In terms of mechanical behavior, if we have an eraser, an halide cube, some soft clay, and honey, what kind of behaviors do they have? So you have to pick the one with the right sequence of mechanical behaviors. So which one do you think is corresponding to the correct answer? All right, yes. So exactly as you mentioned, the eraser is the for the elastic. The halide is brittle, the clay is ductile and the honey is viscous. It's like it's a fluid. So perfect, perfect, perfect. So now can you write in the chat or tell me important parameters that are controlling the material mechanical behaviors in general? Yes, temperature, good one. What else? Somehow, viscosity, yes, even though you will not see it listed in this controlling parameters, basically because um, sometimes people just mention the composition of the material or its properties in general, but they do not include viscosity directly, even though obviously different viscosities means that you're going to have a different amount and ways of deforming. For pressure, yes, definitely. Time of deformation, yes. I don't remember how it's phrased in the course. It must be something like the time scale of deformation. But yes, exactly. This is very important. Do we have some others? Yes, definitely. For the structure, it's part of those properties of the material, but definitely going to have an impact. Um, if it's heterogeneous or homogeneous, it will as well. It will have some impact on the deformation, definitely, and on the mechanical behavior. All right. So I think you mentioned the principal one in the course. You also have the magnitude of the applied stress or force on the material, which would be the last one, basically. And this will change also your mechanical behavior. All right. So, do you know some viscoelastic models that what you've seen in the course? Do you remember the names of those viscoelastic models? Yes, Kelvin Voigt, definitely a very important viscoelastic model. Which do you have other ones? Yes, Maxwell, very good. These are the two most important ones. Do you remember some others? Yes, burger or burgers, exactly. Burgers model, that's one of them. All right. I think inside of one of the slides, you have the moment where you do these constitutive relationships for the different models. And I think you have a special kind of model at some point, which is called the SSL, the standard solid linear model, which will be like one of the models of the viscoelasticity that you have, at least like its name or the configuration of the viscoelastic parts inside of the course. So it would be like four that you have that are quite well-known models. They basically arrange the viscoelastic parts in different ways, giving a different response in terms of stress and strain. So here we have some kind of little questions about how the models are going to behave. So the first is for the Maxwell, and we are going to apply some stress, constant stress for some time. And I would like you to tell me which of these propositions are true or correct. There might be more than one actually in for this. So let me know which one is the correct one, which ones are the correct ones. There are more like than one right answers here in this question. Don't hesitate to tell me A, 2 points, ta ta ta, because something very simple, very short, in order to move forward. Yes, all right. So this is the first step. Let's say R is okay, A is okay because of this um, instantaneous response of the spring, definitely. So what else can you tell me between B, C, and D? Yes, 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 yes. For the B, so for the B, you will have, but one of those characteristics of the plastic and viscous behaviors as well. As long as you apply some stress, you're going to obtain some deformation. There is no real limit a priori to the amount of deformation that you can obtain as a result. I mean, you don't see the mantle, for example, stopping at some point in its convection because it reached a maximum of deformation. Um, as long as there is stress, you can or force, you can get some deformation. So A and B, and there is still one that is correct between C and D.
I would say D makes sense.
All right. Yes, D is good. Basically, B and D are a bit, well, in my head, they are a bit the same. They are like it's basically one of the properties of fluids to be able to sustain some deformation almost indefinitely. Yes, they have no resistance to changes of shape. So basically, they are going to be deformed like this continuously when they are subject to some um, to some pressure or to some stresses. So here, A for the reason that you mentioned. B here I didn't put A, of course, because it's like on the long term. Yes. Then you have B and you have D. Yes, exactly. So here you have another configuration. You're still with Maxwell, but now you're going to take the model that maybe had like 10 centimeters. You're going to extend it to 20 centimeters like this, and you're going to hold it at this position, and you have to tell me what's going to happen. So you take it to a specific deformation and hold this deformation constant like this. So what's going to happen for this model? And here also, I think there are more than more than one correct answer.
It could be A. Teacher, you are muted. Your mic isn't on.
Okay, yes. Sure, but why would that be? Can you give me a nice explanation?
Teacher Laura, help me in the chat.
Sure, but what can you tell me more about this deformation? It's true that you have this time-dependent behavior of the dashpot, but if I hold my my deformation constant like this, what does it mean in terms of deformation inside of a system?
Laura again answered in the chat.
Okay, playing a bit with teams. All right. While the spring would still want to return to its original position, while the spring would like to remain as it is, would be divided between these two elements. Well, as a general rule, it will be, but actually, the answer to my um, to my um, to my question is actually within the question that you have right now. Um, with the Socrative, except A, which I confirm is a good option. Which of the next answers would be right? B, C, or D? Actually, it's part of the explanation. So if you tell me D, can you explain me a little bit how this can happen? All right, I'm not sure if you are trying to write something because well, it doesn't tell me. But in this case, yes. So in this case, for this question, you have A and um, and uh, and D. So basically, when you have A, it's like okay, okay, sure. Well, that's a good way to do it. The You have to imagine that well, if A is true, which is correct, the explanation for A is basically the D over here. If you have your model that is at a specific length after deformation like this, um, just after extending your model, as you mentioned to me a bit earlier, basically the first reaction is going to be to have the spring extension, because that's the one that can react to the deformation instantaneously. So you will have all of the deformation inside of the spring. But you know that when there is some stress, there is going to be some deformation inside of the dashpot. It just doesn't happen um, instantaneously. So when you deform like this, you will have some stress inside of your system. First, the deformation is going to be inside of the spring, but due to this stress, you're going to accumulate little by little some deformation inside of the dashpot. So if you accumulate some deformation inside of the dashpot, it means that you're releasing some deformation from the spring. And as you know, the deformation that you have inside of the dashpot is permanent. So whenever you have some deformation inside of the dashpot, you release some stress as well. Very different from the spring, because the spring, you charge it, let's say, with your stress. It deforms, but it stores that stress within some kind of potential energy like this. So basically, it's not lost. The stress is not lost. It's stored inside of the spring. On the contrary, when you have the dashpot releases the stress while it's deforming. So this exponential decay like this of the stress is because of the effect coming from the deformation of the dashpot and the transfer of that deformation from the spring to the dashpot, basically. So, well, as you know, the speed at which the deformation is occurring depends on the amount of stress for the dashpot. So basically, when you release some stress over time, then the dashpot deforms itself like it's going to be slower and slower and slower and slower over time. That's also why you have this exponential decrease of the stress, meaning that it's not going to decrease this with like by the same rate over all times. Do you see what I mean? Do you guys see what I mean?
Yes, yes, at some extent.
Okay. To me, it's relatively important that you get some intuitive understanding of how this kind of model works. Basically, trying to answer these questions. Basically, so if I do something to a model, what's going to happen? It works relatively well um, for the simple models like the Maxwell and the Kelvin. When you have like 7 things together, it becomes a bit more complicated. All right. So for the Maxwell now, we are going to take the Maxwell model. We are going to deform this model due to some stress, but then we are going to release the stress. So what's going to happen?
I think B is good.
Are you sure? Because we put some stress on the model, leading to some deformation. Maybe we kept that stress for like I don't know 10 minutes, and then we removed completely the stress on the model. Yes, so we extended it a little bit, and then we leave it be like to see what's going to happen. So what's going to
Okay, then I will say A.
okay.
But Juliana also answered in the chat.
Okay, so Juliana put basically B and C, I think, if I read correctly. So everybody agrees with Juliana in this case? No, it's okay. Well, I was just wondering if everybody basically agreed with you, just to make sure that that you're on the same page. Yes, B and C. These two are the right ones. Just well, one of them has the elastic behavior, the other one has the viscous behavior. You know that elastic goes back to its original shape. You know that viscous doesn't. So in this case, just a classic application of those two mechanical behaviors. There is no special tricks. All right, so this one we are not going to do it. Better go to the Kelvin void viscoelastic model. So remember what's the Kelvin void? Instead of having the dashpot and the spring in series, we have the dashpot and the spring in parallel, like this. A small change that changes everything, basically. So if we are going to do this a bit the same, so if we apply a constant stress for some time, what's going to happen to the Kelvin void model? Here you have two good answers as well. Everybody agree?
Yes, it makes sense.
Okay. Yes, in this case, yes, Kelvin void share, how can I say this? It share the stress, and but the deformation is going to be the same, exactly between the two parts, like this. All right, definitely. So, and what about if after we apply some stress for some time, we release the stress that we applied to the model? What's going to happen? Here there is only one correct answer. Can you explain me why? Why would be D?
I'm also with Juliana. She has the right answer, I think.
Yes. How can you explain it with your own words? See, yes, exactly. So the little things that I was mentioning a bit earlier, just like you mentioned, when you deform the spring, you basically store some stress inside of the string. So basically, whenever you release this stress, the spring wants to release that stress as well. But since it's like with the dashpot that cannot actually release instantaneously, it's like cannot deform instantaneously. So the spring is going to act on the dashpot in order for it to go back to its original shape. But since they are tied up, then it's going to force the spring, the dashpot, to go back to its original shape as well. So obviously, since you release little by little stress due to the deformation of the dashpot, the same is going to happen. You're going to have some kind of an exponential decrease of the deformation as well. So it's going to happen faster at the beginning and slower at the end. So do you remember what is the Maxwell relaxation time? Maybe, maybe not.
Yes, I find the answer is the characteristics time scale of which the stress decay when the Maxwell material is suddenly deformed and held to a certain strain. Oof.
Well, I'm not sure I understood completely, but yes, it's like a characteristic time whose mathematically you just divide the stress by a certain amount, which is the exponential number. So that's what uh, corresponding to this Maxwell relaxation time mathematically. More like physically, how it's used is basically a way to separate um, processes taking different amounts of time in order to know if one is elastic, if one is viscoelastic, and if one is completely viscous. So this Maxwell relaxation time is used in this way in order to know what's the dominant mechanical behavior of your process. So as you know, for Maxwell, the mental, for example, follows the Maxwell mechanical behavior. And so for very short time scales, very much shorter than the Maxwell relaxation time, you're going to have a mostly elastic behavior, like for seismic waves. On the other hand, for processes that are very long, like the convection, you're going to have a complete viscous behavior. And in the middle, for this is a time that you can calculate with the Young's modulus and the viscosity of the mantle. For example, you will find that processes of the order of thousands of years are basically in the middle and going to have like a viscoelastic behavior. So typically the glacial isostatic adjustments, for example, this post-glacial rebounds, all of those processes are going to be viscoelastic because the time scale is quite close to the Maxwell relaxation time. So it's an interesting it's an interesting time for this kind of application. Okay, so I just mentioned that. Do you have some questions?
No, not at all.
All right. Okay. So I'm going to lose this presentation of this thingy. I wanted to ask you guys about. Okay, I'm gonna see if I can share this kind of things with you guys. All right, just a little moment. Okay, what is it? Okay. All right. Okay, I cannot share it like this. I'm going to share it another way. All right. So this model that you see is the Burgers model. I think it's like one of its how can I say this standard shapes like this. So I saw that in your Tarayan number 3, you have to do like to find the constitutive relationship for a specific model, which is something that it's kind of a classic in order to well, for this kind of exercises. It's very, very important, these constitutive relationships, because that's what you're going to use in order to predict the evolution of stress or strain over time for a specific model, and then calculate what's going to happen. So even though it looks a bit like a pain to do it, it's relatively important. It's not something that you do because you have to do if there are like some real applications for that. I don't know if you did the exercise in the course to find some constitutive relationships for models other than Maxwell and the Kelvin void, but we can try to start with this model until the end of the class, and you can apply the same kind of steps in order to do the exercise inside of the Italia, which is for another kind of model. So when you see a model like this, what would be your first step in order to find the constitutive relationship? Did you guys do this kind of exercise already inside of the course? Hello? Okay, so I'm going to show you something first. Okay. Poof poof. Okay, so it's not ready there. Poof poof. So for the, you remember this this presentation. For this, and you found some of these constitutive relationships for the Kelvin void, and for the why is it like this? For the Kelvin void and for the Maxwell. So basically the idea is to find a relationship like this one. And I was wondering if you did the application with other models like those ones, for example. Or if you didn't do it yet. Okay. All right. Poof poof. It's just that if you didn't do it, then starting with this other model is a bit more complicated. But why not? Let's try to. I'm just going to explain a little bit the different steps that I use generally in order to do this kind of exercises. So where is it? Here. All right. So here I have this model, which is the burgers model. I think there are like different flavor of this burgers model, but this one has so a specific, well, it has two dashpots like this, here and here, and two springs, one here and one here. And so you can also divide this model in different parts. You have parts that are in series, these three parts, for example, and you have one part that has two components in parallel. So the constitutive relationship to find is the one that you see here. It's a bit more complex than what you've seen before for Maxwell and Kelvin, because there are more elements. And so you have, for example, a mix of the stress and the strain and the different derivatives of the stress and the strain like this, and some the different parameters corresponding to the different objects, so the viscosities and the Young's modulus. So the idea is, in order to do it right, let's say, is to first gather all of the different things that you know about this model. So if you have like a model in series that then you know that you're going to sum the deformations, and you're going to equate the stresses like this because of the setup that you've seen in the case of the Maxwell, which is also in series. For the Kelvin, you know that you equate the deformation and you add up the stresses like this. So basically, one of them is summing up the deformations and doing a little equal to the stresses, and the other one does the opposite. Once you set up these small equations that you have over here, then you can gather all of the different small constitutive relationships corresponding to the different parts. So for example, if you have the stress in a viscous part, you're just going to put the viscosity and the strain rate for this part. You're going to have the Young's modulus and the strain for the elastic parts. And you do it for all of the different elements. So you have 4 elements in this model, 1, 2, 3, 4. So you should have 4 all of those little elements. So you will have 1, 2, 3, and 4. Sometimes when you see that you have some equalities that you can use, then for example, you can replace some of them here by the deformation of the whole element. So that's what I did over here. Sometimes you cannot, and that's what is for this part over here. Once you have all of these problems set up, it's relatively easy to find the answer, because you just need to gather everything and to rearrange the equation so that you obtain the final answer. For example, here I took the rate for everything. When you put the different parts, you replace, you do something little minus, plus, tag, you rearrange, and you obtain your final answer like this. So this one, for example, is for a model that is a bit more complicated that you have inside of the homework, but the process to do it would be the same, basically. So that's why it's a bit. I hope that you got the idea of how to do this kind of exercise. So do you have like a quick question before we finish?
No.
All right. So I hope that you enjoyed doing this kind of thinking for these different rheological models. And well, you will be back with Jill next Tuesday, then I think, for the geodynamics, for some special topics. So have a good day, and see you around. Ciao, todos.